Welcome to History Explained, where we illuminate the past to better understand our present. I'm your guide to your daily journey through the past to empower the future. Today is Sunday, June 8, 2025. As we do every Sunday, we're exploring a revolutionary innovation that has fundamentally transformed how we live, work, and communicate in the modern world. Today, we turn our attention to the transistor, a tiny electronic device that sparked the digital revolution and made possible virtually every aspect of our contemporary technological society. Invented at Bell Labs in 1947, the transistor replaced bulky, unreliable vacuum tubes and became the foundation for everything from pocket radios to smartphones, from early computers to artificial intelligence systems. What makes the transistor particularly remarkable is how this seemingly simple device, essentially a switch that can control electrical current, enabled the miniaturization and mass production of electronic devices that would have been impossible with previous technologies. The transistor didn't just improve existing devices, it made entirely new forms of technology feasible and affordable. So let's explore the development of this world-changing invention, examining the scientific breakthroughs that made it possible, the brilliant minds who created it, the initial challenges in bringing it to market, and the cascading technological revolution that followed. To understand the significance of the transistor, we must first examine the electronic landscape that preceded its invention. In the 1940s, electronic devices relied primarily on vacuum tubes, glass bulbs containing electrodes that controlled electrical current in a vacuum. These tubes had been the foundation of electronic technology since the early 1900s, enabling everything from radio broadcasting to early television. However, vacuum tubes had significant limitations that constrained the development of electronic technology. They were large, often several inches tall, making miniaturization impossible. They generated substantial heat, requiring cooling systems and consuming enormous amounts of power. They were fragile, burning out frequently and requiring constant replacement. And they were expensive to manufacture and maintain. These limitations meant that electronic devices in the 1940s were necessarily large, power-hungry, and unreliable. Early computers like ENIAC contained thousands of vacuum tubes, filled entire rooms, consumed as much electricity as a small town, and required constant maintenance as tubes burned out regularly. The idea of portable electronic devices was essentially impossible with vacuum tube technology. The scientific foundation for the transistor lay in the emerging field of solid-state physics, which studied the electronic properties of solid materials, particularly semiconductors. Unlike conductors such as copper, which easily carry electrical current, and insulators like rubber, which block current entirely, semiconductors have properties that can be modified through the addition of tiny amounts of other elements. The key insight was that by carefully controlling the purity and composition of semiconductor materials like silicon and germanium, scientists could create materials whose electrical properties could be precisely controlled and even switched on and off. This understanding emerged gradually through the work of numerous scientists in the 1930s and 1940s, building on earlier discoveries about atomic structure and electron behavior. World War II accelerated research into semiconductor materials, particularly for radar applications. The military need for better radar detectors led to intensive study of crystal rectifiers, devices that converted alternating current to direct current. This wartime research provided crucial knowledge about semiconductor physics that would prove essential for transistor development. Bell Telephone Laboratories, the research arm of AT&T, was the perfect environment for transistor development. Bell Labs had assembled an extraordinary collection of physicists, chemists, and engineers working on telecommunications problems, and the company's monopoly position provided resources for long-term fundamental research that might not yield immediate commercial applications. The transistor emerged from a systematic research program led by Walter Brattain, John Bardeen, and William Shockley, though tensions between team members would later complicate the story of its invention. The project began with Shockley's theoretical work on semiconductor devices, but the actual breakthrough came through the experimental work of Brattain and Bardeen. On December 23, 1947, Brattain and Bardeen successfully demonstrated the first working transistor. Their device consisted of a small piece of germanium with two closely spaced gold contacts pressed against its surface. When a small current was applied to one contact, it could control a much larger current flowing between the other contact and the germanium base, creating amplification, the key function that made electronics possible. This point contact transistor, was crude and fragile, but it demonstrated the fundamental principle that would revolutionize electronics. Unlike vacuum tubes, it was solid, generated little heat, consumed minimal power, and could potentially be made very small. Most importantly, it could amplify electrical signals just as effectively as much larger and more expensive vacuum tubes. The name, transistor, was coined by Bell Labs engineer John Pierce, combining transfer and resistor to describe how the device transferred electrical signals across a resistive material. This name captured the essence of the device's operation while creating a distinctive brand for Bell Labs' revolutionary invention. However, the initial point-contact transistor had significant limitations that prevented immediate commercial success. It was difficult to manufacture consistently, had poor frequency response for radio applications, and was sensitive to temperature changes. These problems meant that early transistors were often less reliable than the vacuum tubes they were supposed to replace. William Shockley, frustrated by being excluded from the breakthrough achieved by his colleagues, worked intensively to develop an improved design. In 1948, he invented the junction transistor, which used a different structure that was more stable and easier to manufacture. Shockley's design became the basis for most subsequent transistor development and established him as a central figure in semiconductor history. The junction transistor used a sandwich structure with layers of differently treated semiconductor material. This design was more robust than the point-contact version and could be manufactured using chemical processes rather than the delicate mechanical assembly required for point-contact devices. However, it still took several years to develop manufacturing techniques that could produce junction transistors reliably and economically. Bell Labs announced the transistor publicly on June 30, 1948, but the initial reaction was surprisingly muted. Most electronics engineers were skeptical of solid-state devices, having spent decades working with vacuum tubes. The early transistors were expensive, limited in their applications, and unfamiliar to engineers trained in vacuum tube technology. The first commercial applications for transistors were in specialized areas where their unique advantages outweighed their higher costs and limited performance. Hearing aids were an early success because the transistor's small size and low power consumption made battery-powered devices practical for the first time. Military applications also drove early adoption because size and power consumption were critical factors in portable communications equipment. The breakthrough that made transistors commercially viable came with improvements in manufacturing techniques, particularly the development of methods for growing extremely pure semiconductor crystals and precisely controlling their electrical properties. These advances, achieved through the work of scientists like Gordon Teal at Bell Labs and later at Texas Instruments, made it possible to produce transistors with consistent performance at reasonable costs. Texas Instruments played a crucial role in commercializing transistor technology. The company licensed transistor technology from Bell Labs and invested heavily in manufacturing improvements. In 1954, Texas Instruments produced the first commercial silicon transistor, which was more temperature stable than germanium devices and better suited for many applications. The radio industry provided the first major commercial market for transistors. In 1954, Texas Instruments partnered with the small Indianapolis company Industrial Development Engineering Associates, IDEA, to produce the Regency TR-1, the first commercially successful transistor radio. Priced at $49.95, roughly $500 in today's money, the radio was expensive but represented a revolutionary breakthrough in portable electronics. The transistor radio's success demonstrated the transformative potential of solid-state electronics. For the first time, people could carry high-quality radios in their pockets, powered by small batteries that lasted for weeks. This portability created entirely new markets and usage patterns, from teenagers listening to rock and roll to professionals monitoring news and stock reports throughout the day. Japanese companies, particularly Sony, recognized the transistor's potential earlier than many American firms and invested heavily in transistor technology. Sony's founder, Akio Morita, traveled to the United States in 1952 to negotiate a license for transistor technology from Bell Labs. Sony's subsequent success with transistor radios helped establish Japan as a major force in consumer electronics. The impact of transistors on the computer industry was even more profound than their effect on consumer electronics. Early computers using vacuum tubes were enormous, expensive, and unreliable machines accessible only to major corporations, universities, and government agencies. Transistors made it possible to build smaller, more reliable computers that could be used in a wider range of applications. IBM was initially skeptical of transistor technology, preferring to continue developing improved vacuum tube systems. However, smaller companies like Burroughs and Philco embraced transistors earlier, forcing IBM to accelerate its own solid-state development programs. By the late 1950s, transistorized computers were clearly superior to vacuum tube systems in almost every respect. The development of the integrated circuit in 1958, independently by Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor, represented the next major breakthrough in transistor technology. Integrated circuits combined multiple transistors and other electronic components on a single piece of semiconductor material, enabling even greater miniaturization and improved performance. This innovation led to Moore's law, the observation by Intel co-founder Gordon Moore that the number of transistors on a computer chip doubles approximately every 2 years. This exponential improvement in transistor density has driven continuous improvements in computer performance and enabled the development of increasingly sophisticated electronic devices. The transistor's impact extended far beyond its direct applications in electronics. The semiconductor industry that grew up around transistor manufacturing became a major economic force, particularly in California's Silicon Valley. The concentration of semiconductor companies, research institutions, and venture capital in Silicon Valley created a unique ecosystem for technological innovation that continues to influence global technology development. The transistor also enabled the development of new scientific instruments and measurement techniques that accelerated research in physics, chemistry, biology, and other fields. Electronic instruments using transistors were more sensitive, stable, and portable than vacuum tube equivalents, opening new possibilities for scientific investigation. In telecommunications, transistors revolutionized everything from telephone switching systems to satellite communications. The reliability and miniaturization enabled by transistors made possible the complex electronic systems required for modern telecommunications networks, including the eventual development of cellular phone systems and the Internet. The space program became another major driver of transistor development. The size, weight, and power consumption constraints of spacecraft made transistors essential for space-based electronics. NASA's requirements for ultra-reliable transistors spurred advances in manufacturing quality and testing procedures that benefited all semiconductor applications. By the 1960s, transistors had largely replaced vacuum tubes in most electronic applications. The cost advantages, improved reliability, and superior performance of solid-state devices made the transition inevitable, though some specialized applications continued to use vacuum tubes for their unique characteristics. The social impact of transistor technology was equally profound. Portable radios changed how people consumed entertainment and information, contributing to the spread of popular culture and the globalization of music and news. The miniaturization enabled by transistors also made possible new forms of personal electronics that would eventually evolve into smartphones and other ubiquitous devices. The transistor's invention also marked a shift in how technological innovation occurred. Unlike many earlier inventions that emerged from individual inventors working alone, the transistor was the product of organized research in a well-funded corporate laboratory. This model of systematic, team-based research and development became the standard approach for major technological breakthroughs. The three inventors of the transistor, Bardeen, Vertain, and Shockley, shared the Nobel Prize in Physics in 1956, recognizing the fundamental importance of their work. However, the relationships between the three men remained strained, particularly between Shockley and his former colleagues, reflecting the competitive pressures and personal conflicts that often accompany major scientific breakthroughs. William Shockley's later career illustrated both the potential and the dangers of scientific celebrity. After leaving Bell Labs, he founded Shockley Semiconductor Laboratory in California, helping to establish Silicon Valley as a center of semiconductor development. However, his difficult personality and controversial views on race and intelligence ultimately overshadowed his scientific contributions. Many of Shockley's employees left to found their own companies, including Fairchild Semiconductor and Intel, creating a pattern of entrepreneurship and talent migration that became characteristic of Silicon Valley. This Silicon Valley model of combining scientific research, entrepreneurship, and venture capital investment became a template for technology development worldwide. The transistor's legacy continues to evolve as semiconductor technology pushes toward ever smaller dimensions and new applications. Modern computer processors contain billions of transistors, each far smaller and more sophisticated than the original devices created at Bell Labs. New materials and structures continue to extend the transistor's capabilities into new realms of performance and efficiency. Emerging applications including artificial intelligence, quantum computing, and biotechnology all depend on the continued advancement of transistor technology. The fundamental principles discovered in 1947 remain the foundation for these cutting-edge applications, demonstrating the enduring significance of the original breakthrough. The transistor also represents a powerful example of how basic scientific research can produce unexpected practical applications with enormous social and economic impact. The solid-state physics research that led to the transistor was initially motivated by understanding fundamental properties of materials, not by any specific commercial objective. This history illustrates the importance of supporting basic research even when its applications are unclear. The transistor emerged from decades of fundamental research in physics and chemistry, much of which seemed to have no immediate practical value. The lesson is that transformative innovations often require sustained investment in basic scientific understanding. As we live in an increasingly digital world, it's worth remembering that virtually every electronic device we use, from smartphones to satellites, from medical equipment to automobiles, depends on technologies that trace their origins back to that December day in 1947 when two scientists at Bell Labs first demonstrated that a small piece of germanium could amplify electrical signals. The transistor stands as one of the most important inventions of the 20th century, enabling the digital revolution that has transformed virtually every aspect of modern life. From the first transistor radio to today's artificial intelligence systems, this tiny device has made possible technologies that have connected the world, accelerated scientific discovery, and created new forms of human creativity and expression. The story of the transistor reminds us that the most transformative innovations often emerge from the intersection of scientific curiosity, technical skill, and institutional support for long-term research. As we face contemporary challenges from climate change to space exploration, the transistor's history suggests that solutions may emerge from basic research areas that seem unrelated to immediate practical problems. Thank you for joining us for this exploration of the transistor and its revolutionary impact on modern technology. Next week, we'll be back with our This Day in History episode where we'll be examining the significant events that occurred on June 9th throughout history. If you enjoyed this journey through history, please like this video, subscribe to our channel, and hit the notification bell so you never miss an episode. We'd also love to hear your thoughts. What aspects of the transistor's development do you find most remarkable, and how do you think this invention continues to shape our technological future? Let us know in the comments section below. For our members, this Sunday we'll have a special roundup of technological developments from the past week with connections to the historical patterns of innovation we've been exploring in this series. Until next time, I'm your guide for History Explained, where we believe that understanding yesterday is the key to navigating tomorrow.